Hello everyone, welcome back to lesson number 9 for Calculus AB. In video number 1, we talked about how we can compare our graph for f of x versus f prime of x. And a really quick summary about that is that if the graph is decreasing, so if f of x is decreasing, right, it's decreasing, it's going down, then the derivative, the value of the derivative is going to be negative, right, because it's decreasing. So my tangent line, wherever I create it, it's going to have a negative slope. So the value of f prime of x is going to be less than 0, which you guys can see would be down here in this graph right here. And then when my f of x is increasing, as you can see here, the value, the slope of these tangent lines are positive. Therefore, my slope will be positive. And anywhere that my slope has, or f of x has a horizontal tangent, then it's going to cross the x-axis at that value. So for all of these examples, we were able to take the derivative or calculate kind of what our slope would be at any value on these graphs. But there are a couple of places where you can't do that, which means it would be non-differentiable. So what does it mean to be differentiable? Well, differentiable means that you can actually find the slope of the tangent line. You can take the derivative of that function and it still be defined. Well, there are three parts where it's not differentiable. And so we're going to show you all three parts with these cases right here. So if we graph the function, the absolute value of x on our nice little graph right here. So we're going to go ahead and graph this little absolute value of x function here. And again, my horrible lines, but you get the idea of what it is. So here we go. So here's our graph for the absolute value of x. So we don't really know how to take the derivative of the absolute value of a function. Well, what we can actually do is look at the slopes of the tangent lines over that interval and then graph them over here. So that's actually what we can actually do for this particular example. So if we look over here from -3 to -2 and -2 to -1 and -1 to 0, notice that the slope of these lines, right, the slope of these smaller lines right here is actually -1. So at -3, I'm going to go to -1. At -2, I'm at -1. I'm graphing the values. Again, that's how we relate these two things together. These are the actual values of the tangent lines at these points. And so again, we're here at -1. And then what's happening right here? Well, as we're approaching, just going back to our limit aspect for a second, as we're approaching 0 from the left, we still have a slope of -1, but we don't know exactly what's going on right here. So we're going to go ahead and just draw ourselves a little line. Okay? Now, if we go to the other side of the graph, we can see, okay, what's happening here? A tangent line maybe here or here or here. Notice that the slope of these tangent lines are actually +1. So if I start over here again at x equals 3, I have a slope that is +1. And then at 2, I'm at +1. At 1, I'm at +1. Again, as we're approaching 0 from the right, we get +1. But again, we're not exactly at 1 here, so we're good to go. So notice that what we've done here is we've graphed our functions. Now, if you look at the actual graph itself, this is not a nice curve. This is a corner, right? It's actually a sharp point. They come together at a really sharp corner. So in this case here, we have a corner, and then we're going to go talk about that here in a second. So at a corner, the function's not differentiable, because if we look over here, we can't actually graph what this slope is. We don't know what it is. If we're looking to the left, it's going to be approaching -1. If we're looking to the right, it's actually approaching 1. So this function, you guys guessed it, is actually just the absolute value of x over x function, which we all know is actually not even continuous here at x equals 1. Okay? So what do we know about this? We know that the derivative does not exist here. We do not have a value for it. It's 1, -1, or somewhere in the middle. So what we can say now is that every corner, it's not differentiable. So I can give you a random graph, doesn't have to do anything, but right here, it's not going to be differentiable. Okay, and the reason why is that the limit as x approaches, let's call this c. So it's not differentiable at x equals c. So let's just say that right now. So the limit as x approaches c from the right of our derivative does not equal the limit as x approaches c from the left of f prime of x. And that just simply means that the slope of our graph approaching it from the right is not equal to the slope as x approaches c from the left of fx. Okay, so that's our very first one. So what you guys just really need to know out of this video is not even necessarily this. We'll get to this part in video 3, is that if you have a graph, just physically look at a graph and you see there's a corner, or we also call this a cusp. Okay, they're kind of the same thing. If you see a corner cusp, it's just not differentiable. Okay, so that's really what I want you guys to get out of this first part, is that anytime you see a graph, corner cusp, not differentiable at that particular value. You don't ever have to justify why. We're just showing you in the notes why it is. Okay, well, let's look at a couple more examples. So where else is it not differentiable? Because there's two other cases we're going to talk about right now. So if we're looking at example number 4, this says f of x equals the cube root of x. All right, so let's just really quickly take a little graph and talk about this. So when x equals 0, y is also 0, right? The cube root of 0 is 0. When x is equal to 1, y is going to be equal to 1. When x is going to be equal to 2, 2 is just the cube root of 2. But when x is equal to 8, right? So somewhere way out here, when x equals 8, then y is going to be equal to 2. So we have a graph that looks like this. On the flip side of that, when x is equal to -1, then our graph's going to be at -1. And then when x is at -8, we're going to be at -2. So the graph kind of looks something like this. And again, ladies and gentlemen, this is not going to be the best picture for it, but you're going to get an idea of what I want you to get out of this here. And we all knew what this parent function looked like, right? This is not a surprise to you at all. Now, I wish I kind of drawn this a little bit better, because if you guys can barely see this, but if you look at what's happening at x equals 0, there actually is a tiny vertical tangent. There's a vertical tangent here. So the graph kind of comes up and goes straight up a little bit and then to the right again. All right, so there's a little vertical tangent at this particular thing. So hold on, I'm going to do one more thing for it. Try to erase it and try to draw it a little bit better, but this is as good as it's going to get. But this is looks a little bit better for it. So if you were looking at x equals 0, you do have a vertical tangent line right here. All right, so that looks a little bit better. And so what does that mean? So we're going to go ahead and write vertical tangent line. Vertical tangent. So why? Why is this not differentiable at this value? Well, let's take its derivative. Now remember, it is value, there's a vertical tangent at x equals 0. So if we take this derivative, of this function, f prime of x, remember this is just x to the 1/3 power, right? So our function is x to the 1/3 power. If we take its derivative, it's going to be 1/3 x to 1 less power, which is going to be -2/3. So if I want to rewrite this again, it's going to be 1/3x to the 2/3 power. And ladies and gentlemen, if I ask you to evaluate this at f prime of 0, you're going to get 1/0, right? You're going to plug 0 in here, you're going to get 1/0, which means that there is actually an asymptote at x equals 0. So now remember, vertical tangent for the function ends up turning into an asymptote for our derivative function. So again, ladies and gentlemen, we can't put a value on this. We don't know what the value is. We don't know what this is. It's undefined, right? 1/0 is undefined, which means that this does not exist. F prime of 0 does not exist. And again, that it's not differentiable at x equals c. So then we would say that f prime of c would be undefined. Okay, undefined. All right, so that's our second one. So we have a sharp corner or a cusp. Again, it's not differentiable if we have a vertical tangent. So we're just visually looking at graphs right now. This second part that we're doing is just showing you guys why that this is not differentiable at that particular value. Because again, this derivative does not have a value. I couldn't ask you guys to tell me what f prime of 0 is. We don't know what it is. We don't know what it is. So let's go ahead and look at our last example. And this one says, consider the piecewise function and its derivative. So we're going to go ahead and graph our function here. And so when x is greater than 4, our value is going to be 3. So when x is 1, 2, 3 greater than 4, our function is going to be greater than 3. And again, I'm going to keep it open because it's not equals to. And then when x is less than 4, then we're going to have the line x equals -3. So let's look at -3. We're going to go ahead and just slope, like so. And we're going to draw ourselves a little line here. So this is what the piecewise function looks like. So to the left of positive 4, to the left we have the line x minus 3, and then to the right of 4 we have 3. So if I want to ask you guys to find the derivative of this, now again, we're talking about what's happening at x equals 4. Okay, that's clearly what's going on here. So we're taking the derivative of this. We're going to say well, the derivative of this function is going to be 1, and the derivative of this function is going to be 0. So just like before, we're going to graph these functions. So when x is less than or equal to 4, so again, 1, 2, 3, 4, when x is less than 4 or equal to it, it's going to be equal to 1, right? So this is going to always be 1. And to the right of 4, it's going to be 0, the derivative. Yeah, we know what f prime of 4 is, right? That's fine, but that's not what we're looking at. We want to talk about the slope. We want to look at what's happening to the left and the right. Just like we talked about with the corner and the cusp, we know that this derivative, if we're approaching 4 from the left, is going to be 1, and if we're approaching 4 from the right, our value is going to be 0. So we know that this is not defined. So f prime of 4 cannot be defined because of what you see right here. This function is, you got it, this is not continuous. So what we can say now about this is this shows us that fx is not differentiable at a non-continuous value. So if it's not continuous, it's never differentiable. So in order for something to be differentiable, it's first of all got to be continuous. And we can go one little step further with this, which means that also the limit has to exist, right? Because in order for something to be continuous, the limit also has to exist. So if we have a limit, we can check to see if it's continuous. If it's continuous, then we can check to see if it's differentiable. Just because it's continuous does not mean it's differentiable. If it is differentiable, and this is why I wrote it this way, if it is differentiable, you can already assume that it's continuous, and you can already assume that there's a limit there. Okay? So let's look at one very basic example. So we're looking at these values of A, B, C, and D, and we're asking, are these points differentiable? Are there points differentiable at these particular examples? And so for example A, we can say no, because it's not continuous there, right? This has a removable discontinuity. So this is a removable discontinuity. Yes, the limit exists. The limit exists at A, but it's not continuous at A, therefore it's not differentiable. Same thing can be said about B. Right? There's a jump discontinuity here. So again, because the word discontinuity, we're also not differentiable at those two values. So anytime it's got a jump, a removable, or an infinite discontinuity, it's automatically non-differentiable. We can go further along and say, okay, well, it's C. This is not differentiable because there's a corner here. It's a corner. Or in this case, you could also think it kind of looks like a cusp. Again, it would be very obvious on the graphs for you guys to do it. So again, not differentiable there. And then the final one is going to be here at D. Again, it's not differentiable because we have a vertical tangent line. Okay, we have a vertical tangent line. And so the wording at the very bottom of your graph here exactly just summarizes what I just said there. So at points A and B, the function is discontinuous, so therefore not differentiable. For C, it says, number 2, it says at point C, the function is continuous, but it's still not differentiable because the curve has a sharp corner or cusp. And then D, it says, for 3, at D, the function is again continuous, but not differentiable because, again, there's a vertical tangent at that point. So that's really all you have to know about this. So let's, coming out of this video, what should you know? If I give you guys any type of graph, and I say, tell me where it's not differential, just from the graph, you just have to look at 3 things. Is there a corner or a cusp? Non-differentiable. Is there a vertical tangent? Again, non-differentiable. Is it continuous? All right, if it's continuous, or if it's non-continuous, it's also non-differentiable. All right, so that's our video number 2. When we come back to video number 3, we're going to use what we've now all learned and talk about how to do this algebraically. So I'll see you guys in the next video.